Okay, great. So let's get started. The way that I think we should do this is, if you have questions that you would like to ask during the talk, then please just put them into the chat, and I will, either call on you or read out the question. And then at the end of the talk, we can have time for questions. And again, maybe you can just, either raise your hand or put a question into the chat, and I'll probably call on you at that point and, just encourage you to ask your question. So let's get started. So it's a pleasure to introduce Lin Lin, who's in the math department at Berkeley and also at Lawrence Berkeley National Lab. Lin is a mathematician who's gotten interested in quantum computing recently and has, done some really interesting work on, many different things, including quantum algorithms for problems related to linear algebra. And today he's going to tell us about quantum linear algebra with near optimal complexities. So please, Lin.
Okay, thank you very much, Andrew. First, since this is the last talk of this quantum seminar, let me take this opportunity to thank all the organizers for the amazing work in this semester. And not only because we're going through such a difficult time, but even in the regular time, I think the activities, I have to say, are very well organized, and I have personally learned a lot. And if I organize or co-organize long-term efforts in the future, I mean, this should be my model, although I highly doubt whether I can do nearly as good. So this is joint work with two fantastic students in the math department, Dong An and Yu Tong, and the archive links of the papers are here if you're interested. What I'm going to talk about are some recent works on near optimal complexity quantum linear solvers. There are two different techniques. One is called adiabatic quantum computing, and the other is called eigenstate filtering. They can independently achieve near optimal complexity. I'm going to talk about what it means. And if time allows, I'm going to talk about some near optimal algorithm for finding the ground energies and some future works. So first of all, I think there is perhaps a widespread belief that a quantum talk should start with a picture of Feynman, even to an expert audience. And so I hope this does the job, and which is if we look at Feynman through a quantum mirror, and this would be a superposition of that. And quantum linear algebra is about solving linear systems, eigenvalue problems, matrix exponentials, least square problems, so on and so forth on the quantum computer. In the past few years, there have been many interesting and exciting progresses along this line. And quantum linear algebra, I think, is a reasonable way towards the quantum advantage, which is beyond the quantum supremacy now, and because that's related to quantum machine learning, so on and so forth. So this semester, I'm teaching the Math 54 at Berkeley. It's the first class of undergraduate students to the linear algebra, and the first class shows AX equals to B. During the semester, I told them that I'm interested in the quantum linear system problem, and they're said, ask what's the difference, and say, what I said was basically you put a bar on the left and put the angle on the right. All of a sudden, you have turned this out and uninteresting problem into an in and interesting problem. Voila. So not exactly, because it's indeed a quantum algorithm has its unique features. All vectors first needs to be normalized. If we say A is a capital N by capital N matrix, B is a vector of size capital N is 2 to the small n, then the vector needs to be normalized without loss of generality. Let's say that the spectral operator norm of A is bounded by 1. Then the solution vector, unlike a classical computer, you just get A inverse times B, you only get a vector that is proportional to A inverse B. And the question, and you can multiply by arbitrary phase, and the solution vector will still be the same thing. And there's also the question of how to get the information of A and B into the quantum computer. This is the so-called reading problem. It's not an easy or trivial problem at all. So throughout the talk, we're going to take this oracular assumption, which means that we'll assume there's a way to put the A and B into the quantum computer. And for a number of type of matrices, we do know how to get them in there. And so we mainly measure the so-called query complexity, or the number of oracles used. And based on the query complexity, with some effort, you can go to the gate complexity, which obviously relies on how you implement the query models, but we won't talk about this kind of thing most of the talk. So to talk about the quantum speedup for solving the quantum linear system problem, we need to worry about the condition number denoted by kappa, and then there's a target accuracy called epsilon, and with some proper assumptions on A, for example, it is D sparse. D sparse means that each row and each column of A has no more than D entries. The oracle should cost like a poly small n, which means it has some foundation to get some speed up. The groundbreaking HHL algorithm gives you O tilde. Throughout the talk, tilde just means that the dependence on the parameters appearing in the parentheses, they omitted some logarithmic contribution. So it's a kappa square over epsilon. And there's a poly n here already suggests there's exponential speed up with respect to the classical solver. But whether we actually can obtain exponential speed up, the answer could depend on your reading and the readout models. There's well-known work now by Yuan Tang, so we're still exploring, I mean, for which kind of problems we do actually get exponential speed up. So, but in the terms of a query complexity, this is the query complexity. Then the dependence on epsilon obviously is not very good. 1 over epsilon. This has been significantly improved by Andrew Childs, Kothari, and Soma through a technique called the linear combination of unitaries, has improved that to kappa square polylog 1 over epsilon. So the accuracy, there's an exponential improvement. And also, if you use a technique by the quantum signal processing done by Lo and Trong, and recently in a very nice paper by Andreas Gein, Su, Lo, and Weeb, and you can achieve O tilde kappa square log 1 over epsilon scaling. So if you compare this with the classical iterative solvers, and for example, we assume the matrix is positive definite matrix, and we measure the error in terms of the A norm, then the steepest descent gives you here the prefactor is n, capital N, which means it's expensive, and here's kappa log 1 over epsilon, which is good. But there also exist methods like a contract gradient, which takes the kappa to square root of kappa, which means quantum algorithms, they're generally expected to scale better in n, but worse in kappa. And in the same HHL paper, there's a lower bound showing that a quantum solver cannot generally achieve less than order kappa scaling. So this kind of scaling is really the best. The so-called near optimal quantum linear solver we're talking about aims at achieving O tilde kappa polylog 1 over epsilon complexity. So there's no polylog kappa here because this is O tilde. So if you remove this tilde, you can put a kappa here as well. Now, first, let me say the basic idea behind this LCU technique and why there is a kappa square scaling. So let's say A is a Hermitian matrix and there is a condition number is kappa. Therefore, the spectrum of A is contained in this region dk, that is -1 to minus kappa -1, kappa inverse. Kappa is bigger than 1, so this is a number that's smaller than 1, the union with this interval. So A inverse is generally not a unitary operator, so you do you can use some other ways to use the unitary operator. For example, you can expand it into a Fourier series. Then each of this is a Hamiltonian simulation problem, and it's a linear combination of a Hamiltonian simulation, therefore linear combination of unitary. This is highly efficient in the sense that if you get m terms here, you only need log m ancilla qubits. The implementation of efficient implementation of, for example, the so-called select oracle requires a little bit more thought, but this is the basic idea. How do you measure the cost of such an LCU technique for solving QLSP? There are two parts. The first part is the cost of doing the Hamiltonian simulation. And here we only measure that for the longest t that you need to do. And the larger the condition number, the longer the t you need. So the cost of the Hamiltonian simulations, OT log t over epsilon, which can be interpreted by some approximation theory to O tilde kappa polylog 1 over epsilon. So this is just doing it once. But it's not like you just do it once and then you're done. This is because you also need to measure the ancillars and make sure that this is correct. What is the probability that the success probability? It is like 1 over kappa, and therefore the number of repetitions in general is O tilde kappa square. And you multiply these two together, you get O tilde kappa cube polylog 1 over epsilon. So it's pretty airtight argument. And there's a standard technique to improve the efficiency, because this is a standard probability and you can use amplitude amplification. You get a square root here. So this is O tilde kappa, multiply them together, O tilde kappa squared. So before I proceed, let me just give an overview of the different techniques that have been developed for solving the QLSP. The original HHL query complexity is O tilde kappa square over epsilon. The LCU is a kappa square polylog 1 over epsilon, as I had talked about before, and the QSP. And so this is kappa square log 1 over epsilon. There's no polylog because the QSP does not have the linear combination part. I need to remark here that the dependence on the kappa can actually be improved, especially by this so-called variable time amplitude amplification method. So with that, the complexity of the HHL can be improved to all the kappa here, although the dependence on epsilon is worse, and here you have essentially the near optimal complexity. But I want to say that VTA is a really complicated procedure, and at least to me. And so the QSP, and to our knowledge, we don't know yet how to, well, at least not in the literature, I would say how to combine that with the VTA. But another feature of the QSP is that you only need to query the right-hand side for O tilde kappa times. There's no log 1 over epsilon dependence. So there's another line of thought to solve QLSP, which is about doing adiabatic quantum computing, which I'm going to talk about in detail later. The groundbreaking thing is the randomization method in 2019, and you can get by Subasi and Soma. So the complexity is O tilde kappa over epsilon. It, instead of preparing a pure state, it actually prepares a mixed state. And again, you can use a technique similar to VTA called the repeated phase estimation. The complexity can be improved to near optimal. But again, this repeated phase estimation is a pretty complicated procedure. And here comes our work. The first one is called the time optimal adiabatic quantum computing, which just achieved the near optimal complexity. And there's no need for any amplitude amplification, even the standard amplitude amplification. And the efficient gate-based implementation relies on TD Hamiltonian simulation. And finally, there's the eigenstate filtering technique, which achieves this complexity without a polylog. And this to me is so far my personal favorite one, which is there's no need for any amplitude amplification. It's a rather simple procedure and does not really rely on any complex subroutines such as VTA, repeated phase estimation, or the time-dependent Hamiltonian simulation. So let me first introduce the idea of using adiabatic quantum computing to solve QLSP. It's a beautiful idea, really that weaves together linear systems, solving eigenvalue problems and differential equations together. So the idea is the following. You have a vector B, you define a projection operator called QB, which is identity minus the projection here. If you have a solution satisfying AX equals to B, you just apply QB on the left. You find that QB AX is QBB is 0. Okay, what does this mean? So this is just a lemma. So how to use this is I form this Hermitian matrix called H1. Here it is AQB, here it is a stagger, and the QBA. I assume the A is, let's say, positive definite. So I look at this vector, x tilde, which is 0x, or writing the more standard form, x is 0. Then I multiply H1 to this x tilde. Then I have 0 times 0, 0 times x is 0, AQB times that is 0. Okay, that's 0. QBAX is exactly 0 according to here. And Q, the other one is, so it is also 0. Therefore, this x tilde lies in the null space of H1. Another thing is there's another vector in the null space of H1, which is this 1b. Let's do it again. So 0 times AQB, QB times B. QB is the thing that projects out the components of B, so that's 0. The other one is 0 plus 0, 0. So the null space of H1 is guaranteed to be of 2 dimensions. So the problem of solving QLSP becomes an eigenvalue problem, which is to find an eigenvector of H1. This one, not this one, corresponding to the eigenvalue 0. Is there any question? Okay, so the idea of adiabatic computation is as follows. You start from a known eigenstate called a psi naught with a known simple Hamiltonian H naught, and you're interested in some eigenstate psi 1 corresponding to a matrix H1, for example, the H1 we just talked about. I just draw a line between the two. So just here's a simple form, and then I propagate this time-dependent, really time-dependent Hamiltonian simulation, solve this time-dependent Hamiltonian simulation problem. And our hope is that when t becomes large enough, and when I reach t equals to 1, and the Hamiltonian really becomes H1, this is the same as psi 1 here that I'm interested in. So the gate-dependent implementation of this procedure is not that simple. You can do time-dependent order. If you really want exponential speedup, you'd better be careful. And also another way to achieve near optimal complexity is given by Low and Weeb in 2019. So the adiabatic computation is an old idea that started from Bohr and Fock in the 1920s. It says that a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough, and there's a gap. So over the past nearly a century now, many people have done analysis of this along the line, but the basic idea is always the same. So I'm interested in a projection operator, which is something around here, which is the PS, and it's gapped away from the thing that I'm not interested in, and therefore I start from here, and hopefully I evolve it slowly, and I reach here, so that this is still within the target subspace. Andrew, did you want to ask a question?
Yes, there's a question on the chat which I wanted to relay. So, and it's maybe on the previous slide. So Anders asks, is the kernel bigger if one aims for only the pseudo inverse?
If the kernel is bigger, yes, I think that will be bigger. Yeah, for the moment, I assume that kappa is finite.
Okay.
Yeah.
Thanks.
Okay. So So the adiabatic quantum computation to solve the quantum linear system problem is the following. The H naught is indeed a trivial Hamiltonian. It only involves the B, has nothing to do with A at all. So H naught is 0, QB 0. You can again study its null space. It has the B bar we talked about before, the B0. The other one, 0B, and the other one is B0. What we want is to start from this B tilde. Okay, it's a 1, 0 eigenvector of H naught, and adiabatically connected to X tilde. And this is what we're interested in. So as you can see, there's only one eigenvector in the null space is of interest, and the gap between this one and this one is 0. However, the transition from here to here, you can simply see that the overlap is always 0, and therefore the transition to B bar is prohibited during the dynamics. Here is an example showing how this works. I just connect 0 to 1. The condition number for this matrix is not particularly large, but you can see throughout the thing, and it is gapped. And I'm interested in this one, which is the 0 eigenvector. And here, what I'm showing you is the instantaneous error at every time. And as t becomes t is 10, the error is pretty large. If t is 100, error is better. T is 1,000, error is even smaller. And you can also measure the fidelity, and the fidelity monotonically increases as you increase the time. So, more quantitatively, first of all, you see that the convergence here is not very fast. This is just a vanilla AQC. There's a more quantitative version of this, which is, I mean, there are many versions of such theorems. One of the, I'm only quoting one of them by Jensen, Ruskay, and Saylor, and which means if you look at the set of Hamiltonians, one parameter family of Hamiltonians on the projector, and separated by a gap, then at any time s from 0 to 1, you can have the following error estimate, which is eta. Eta has a bunch of terms. There's basically it takes the form of the time derivative of h, some order, can be first order or second order, divided by a power of the gap. So what it says, if the gap is small, the error is large. If the Hamiltonian evolves too fast, the error is large. Okay, and second is that the t always appears here, which means that generally we expect a 1/t convergence. It won't be very fast. You just want one extra order of accuracy, increase t by order of magnitude. So if you assume the gap is uniformly bounded by some number, let's say delta star, then the t will be the worst case bound, and this is the worst case term, will be delta star to the minus cube divided by epsilon. So it's a pretty bad error estimate, and you don't really want to use it. Now the question is, what is this delta star? The delta star, as you have seen before, can get pretty small, and this kappa is not that large. And if kappa gets larger and larger, this gap will get smaller and smaller. More quantitatively, you can easily get a bound, which is this delta star. S takes this form, and it's going to be bounded by kappa to the -1. So if kappa becomes really large, the gap becomes really small. So the worst case time complexity t is going to be order kappa cube over epsilon. So the key idea behind this AQC-inspired algorithm by Subasi, Soma, and Osutsky last year was the so-called randomized method, is to use something called a rescheduled dynamics. I'm going to talk about the rescheduling later, but if you measure the two-norm error of the density matrix, they have developed a method to improve the scaling from here to this one, which is a pretty significant improvement, especially in terms of kappa, although the accuracy on epsilon is still 1/epsilon. So what is this rescheduling? So what inspired us to look at this problem is we're interested in this randomization method. First of all, is not like AQC at all. If you really look at the algorithm, it's more related to another technique I'm going to talk about later called the quantum Zeno effect, and Andrew is an expert on that. And what we're interested in now is to accelerate the vanilla AQC to make it better. So whether there's a chance to salvage the AQC and to use it for doing the QLSP. So the goal is to improve the scaling of AQC with respect to kappa. And the idea is very simple. Instead of putting an S here, I put a scheduling function called fs here. So the line connecting from 0 to 1 is 1 minus fs plus fs times h1. And the time-dependent Schrodinger equation still looks like the same. And the starting point is this b tilde, which is the eigenstate of h naught. The scheduling function should satisfy some simple constraints, such as it's bounded by 0 and 1. But 0 should be 0, and 1 should be 1. And if you look at the error analysis, the idea is that the error bound always takes the form of some h to the derivative divided by delta. So what it means is that when delta, the gap, becomes small, h should be slower. That's it. And you can expect that there is some cancellation. And this idea is not new, has been pioneered by Roland and the Cerf for the first time, showed the so-called time optimal AQC for the Grover search. Because if you compare the standard Grover algorithm and the AQC, you can find there's a square root of n gap, and Roland and Cerf first fixed that. So what we're taking this scheduling is not a new schedule either. It's developed by Jensen, Ruska, and Saylor, also mentioned by Abash and Leider in 2018 IMP paper. And it satisfies the following ODE. The form of the ODE is not that important. You can look at the picture. So this one is a straight line, which means that it just go uniformly in speed. The AQC is parameterized by a factor, by a parameter P. P takes the value from 1 to 2. And so roughly, they all share the same feature, which is at the beginning, when the gap is large, remember that. So at the beginning, the gap is large. In the end, the gap is small. So what you do is, when the gap is large, you go faster. And when the gap is small, you go slower. That's it. And then through some error analysis, you can prove that this just simply reduces the complexity to order kappa over epsilon. And there's not even log factor when P is chosen to be between 1 and 2. And if P is indeed equal to 1 and 2, you get this kappa log kappa over epsilon, which is the same as the RM method. So this one, I assumed H is positive definite for simplicity, but the similar results can be done for indefinite and non-Hermitian matrices through the standard dilation tricks. So now we have solved the kappa problem, and the kappa order kappa accuracy is already near optimal due to the complexity lower bound. We want to improve the accuracy with the dependence on epsilon. So there's yet a different scheme called we developed called the AQC EXP. So it's a modified schedule, and this schedule has been a similar version of the schedule was proposed by Nancy in 1993. So the shape of the schedule looks like this. A little bit funny. So instead of saying that, I mean, at the beginning it goes fast, you can see both at the beginning and at the end, and the schedule is very, very slow due to this kind of exponential minus 1 over s type of behavior. And the intuition behind is again from the error bound of the Jensen 2007 paper, because you can see there's some h, some derivative at the beginning, some derivative at the end. In the middle, you have a bunch of integral, and by integration by parts type of argument, you can get a super algebraic convergence. You can boost this up and make the rigorous error analysis to the exponential convergence, and this is following the idea of the Nancy 93 paper, and which is based on asymptotic expansion of the projection operator. So you can indeed prove, so there's some complicated dependence, but indeed T depends near optimally with respect to kappa, and here you have a polylog kappa over epsilon type of dependence here. And indeed, it achieves near optimal complexity, and again, similar results can be achieved for more general matrices. And this type of AQC for solving QLSP has implications on another technique called a QAOA, or quantum approximate optimization algorithm. The idea of a QAOA is very simple. You have two matrices. One's called a driver, the other is called a mixer, just two names, of H0 and H1. So you just alternately apply these things, and with some beta 1, gamma 1, beta 2, gamma 2, so on and so forth, applied to some initial state. And you can obviously see the connection between the adiabatic quantum computing and the QAOA, because you trotterize the AQC. This gives you a natural implementation of QAOA, although it's not necessarily the best one, because it rigorously follows the adiabatic path. The QAOA allows some hybrid quantum classical optimization. So if you can do the classical optimization well enough, then this is guaranteed to have time complexity no higher than that of adiabatic quantum computing. So the optimal protocol of the QAOA and should also obtain the near optimal complexity, because the upper bound is given by time optimal AQC. And but there is an important difference. So recently in Gorshkov's group and showed, but also other groups as well, showing that QAOA is expected to follow a non-adiabatic shortcut, although the understanding of such a non-adiabatic shortcut is rather poor, I would say, at this moment. Let me show you some numerical examples, and this is applied to a positive definite matrix. And although we're measuring the fidelity, and although the RM method is, kappa, log kappa over epsilon, but the pre-constant in terms of the fidelity is actually huge. And you can see that it's even worse than vanilla AQC. I want to say that this is very much related actually to the fact that they are preparing the mixed state, and therefore there's a big difference between the error measured by the 2-norm and measured by the fidelity. And the AQC1, which is only one of the method, and the time is like this. There's a huge difference between these methods. And AQC1, remember that it also has a 1 over epsilon type of dependence. And now, if I look at the higher fidelity, I cannot plot the vanilla AQC and RM anymore because it's on top of the roof. And we start from AQC1 here. And then this systematically go down. The best AQC type method is achieved by 1.75. And AQC EXP, which is the better one, right, actually is the worst. And this is because the accuracy is not that high. And we're talking about fidelity 0.999. QAOA has the lowest time complexity by definition, but the optimization is at least quite painful. And if you really want to see the power of AQC EXP, you need to tune your accuracy down, 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 down. And these things, they indeed scale like a like linearly. And you can see that AQC EXP scales beautifully. And here it's indeed achieves exponential convergence. By the fact that QAOA should be no worse than any AQC, this is also like a polylog dependence with respect to epsilon. And you can look at the tables, and I will skip this thing. And you can do the non-Hermitian matrices as well. The behavior is rather similar, and the behavior for the epsilon part is also rather similar. So let me see. So okay, so maybe let me pause. There's
a question. There's a question in the chat. Maybe this is a natural point.
Yeah.
But this is from Jiancheng Li.
Okay.
They ask,
what if the matrix is not full rank? Is there any correspondence between AQC and the pseudo inverse? I think that's a great question. And important thing is whether it prevents the the transition from the stuff you want and the thing you don't want. The transitions are prohibited. Naively thinking, I think they're not prohibited, but maybe there are techniques to make it work better. Yeah, it's a good question.
Okay, thanks.
Yeah. Any other question? Okay, so let me talk about the second part. How am I doing with time?
It's 2:36.
2:36. Okay, sounds like good. So the next one I'm going to talk about eigenstate filtering, which is a different technique to achieve the near optimal complexity. Here I'm using the now famous block encoding model. I like this really a lot. So like before, I haven't even talked about how to really deal with the reading problem at all. So that's like a black box. Block encoding is not really exactly a black box. It's like a gray box. And what it does is to say that you have a matrix A, which is a capital N by capital N, and it's a non-unitary. I want to put it somewhere inside the unitary matrix. Let's say 2n by 2n. What it means is that I put this matrix A to the upper left part of this matrix. In this sense, UA block encodes A, which can be non-unitary. So the question is, you just give me an arbitrary matrix A of size n by n. Can we find such a UA so that A is the upper left block of this UA? And this is the so-called block encoding problem. Clearly, it is not possible if the spectrum norm of A is too large, because this one, all the singular values are 1. So this gives rise to the proper definition of block encoding. You give me an n-qubit matrix. If I can find a number alpha, which is used to scale the matrix A, you can think A divided by alpha here, and epsilon, which is the error. It may not be possible that I can exactly block encode this matrix. And I may not be able to exactly encode that with only doubling the matrix size or just one extra qubit. I might need m ancilla qubits. So there's a three-way pruned generalization, alpha, epsilon, m. So if I can find such a UA such that by by projecting out this UA with respect to this is 0 to the mth power, and right, this is correct. So this is times identity here, so operator, and A divided by alpha or multiplied by alpha here, the difference is bounded by epsilon, then UA is called alpha m epsilon block encoding of A. If this is the first time you see it, it's quite a mouthful of things, but it's really quite a natural definition. For example, if m equals to 1 and UA would become A tilde here, if A minus alpha times A tilde is bounded by epsilon, it's called alpha 1 epsilon block encoding of A. It's a very powerful model, and many examples, many matrices can be done through the block encoding, like density operators, POVM, D-spots, so on and so forth. And many of you have seen talks by Andreas during the semester. So quantum signal processing, roughly speaking, is a way to compute matrix functions. So many tasks in linear algebra can be done with matrix functions, and especially when A is Hermitian with this eigenvalue decomposition, the matrix function can be defined like this. And the quantum signal processing is a pretty powerful, general, and low-cost tool for computing the block encoding of FA, where F is a complex function, usually a polynomial, satisfying some parity constraints. The actual constraints are quite technical, but are relatively natural as well. So you can also generalize it to the so-called quantum singular value transformation. And the circuit is really, really simple. Once you have a block encoding called UA as well as U dagger, most of the time what you're going to do is this. You just interlace this UA and the UA dagger with some controlled phase vectors and always look like this. So the so-called eigenstate filtering problem is one particular matrix function. And you start from a Hamiltonian H, which is Hermitian. Lambda is eigenvalue of H that you're interested in, which is separated from the rest of the spectrum by gap delta, which is like this one. So this is the eigenvalue you're interested in. What you want is to keep this part and throw away the rest of the parts. And you do know at least the lower bound of the gap. So lambda is separated from away the rest of the things by delta. You want to construct a spectral projection operator, which is 1 here and 0 here. But this is a discontinuous function and it's difficult to do. But since there's a gap, there's a good chance that you can just make a smooth transition from here to here and without losing much accuracy. This is the so-called eigenstate filtering problem. What we did is roughly say if you want to restrict it to the polynomial type of approximation, we get the best polynomial type of approximation with this number of controlled unitaries and this number of primitive gates. So the basic idea is the following. It's an old idea that is the min-max polynomial based on the Chebyshev polynomial. So, I mean, if you look at the textbooks like Yusuf Saad, you will find that if I want to do the eigenstate or one-sided eigenstate filtering, the best polynomial is achieved by the Chebyshev. And this one, I want to get a two-sided thing. I don't want this part, don't want this part. I want to keep this one, and wanted to satisfy the min-max property, which means the error should be distributed. So reach the maximal error here, and so on and so forth. And this is the polynomial. You can prove that this is the min-max polynomial, and you can combine this thing with the quantum signal processing to implement that, which gives the previously aforementioned complexity result. So you can use the eigenstate filtering to accelerate any AQC type of technique to solve the QLSP. Why? Because we have said that the idea of adiabatic quantum computing is to convert the linear system problem to an eigenvalue problem. What you want is to find a 0 eigenvalue here, and you don't want the negative ones, don't want the positive ones, you just want 1 here. So let's say I do AQC. I just run it to some constant accuracy, let's say 0.5, okay? But this is a non-trivial. I've already done that. So the complexity of the AQC is something like this. And I achieve a solution with the epsilon to be of order 1 accuracy. So this one can be thrown away. I obtain this X naught with some effort, which is kappa log kappa. Now I apply eigenstate filtering on top of that. So you already obtained a pretty good initial state, which has a decent overlap with the final state, because this is the requirement. Now I just apply this polynomial filtering, and that's it. You can prove that this achieves the near optimal complexity, which is the number of all queries to A is order D. D is the D sparse, which can be neglected, kappa, and all the rest of the things are logarithmic. So this is the total query complexity, but you can have the gate complexity as well. So to show you some numerical results that this indeed works for if you, let's say, start from AQC guess, you can see that the initial error is not infinite. I mean, it's something. And then you just increase L, and indeed you get exponential convergence. And the growth with respect to kappa is indeed very close to linear. The next technique is that, as I said, so there are actually 2 uses of eigenstate filtering to solve QLSP. So in total, I'm introducing 3 near optimal algorithms to solve QLSP. One's AQC EXP, the other is the combination of eigenstate filtering with AQCP, and the third I'm going to show you is this quantum Zeno effect. Quantum Zeno effect, I mean, it's a little bit difficult to explain, and I certainly wouldn't be able to explain better than Andrew, so I wouldn't even try that. Let me just say that quantum Zeno effect is a very close cousin to adiabatic quantum computing. The basic idea is the following. So you just say X bar is your adiabatic path. You don't know that a priori, but you know that exists. And you go from the beginning F0 equal to 0 to Fm, m is the big number, and Fm is equal to 1. If you think this m is large enough, and the distance between each consecutive Fi and Fi plus 1 is small enough, and you keep measuring on top of that, okay? So it's a crazy thing. So you just keep doing the measurement, and you can prove that this is roughly doing the AQC. You can drive the state gracefully from the ground state here, which is a 0b, to the end, which is the thing that you want. So at each step, you measure the state, you project that to the individual intermediate eigenstate of HF, and in the end, the fidelity approaches 1, which is the stuff you need in the end as the step size decreases, as if you are increasing the time complexity of your AQC. So the idea, therefore, of using the combining eigenstate filtering and QZE to solve quantum linear system problem is to replace this measurement procedure by the projection procedure done using QSP and the eigenstate filtering algorithm. So you can analyze and showing that doing it carefully along the rescheduled dynamics, and the success probability is omega 1. So in principle, you only need to repeat this with 0.1 times. This is really the key, because if you think about QSP or linear system problem, or LCU, it's not like each individual run is that expensive. Each individual run is order kappa or O tilde kappa that is expected. It's really that you have to repeat it for many, many times. That gives you the kappa square complexity. And this QZE and really allows you to do it essentially with 0.1 times, and then you're done. And this is the key, and the complexity is like this. There are a few, I would say, pretty salient features of this approach. Is fully gate-based implementation. All you need to do is to prepare the intermediate Hamiltonian, start from initial state, which is a 0b, and you keep doing this kind of a filtering implemented with a QSP circuit. You just do it for a few times, and in the end, it's a success, then you're done. Okay, so really simple, relatively, I would say, simple procedure to achieve the near optimal complexity. And all we need to do is to successfully project along a carefully scheduled adiabatic path. So any question? Is there something in the chat? Or...
There was a question in the chat, which I think was about the previous part, and maybe we'll save it for the end.
Okay, sounds good.
Yeah.
Okay.
I think
Finally,
on now.
Okay, so finally, let me talk about another thing, since I'm talking about quantum linear algebra, not just quantum linear system problem, is to find the ground energy. So the ground energy, I mean, is very much related to the eigenstate filtering problem. Eigenstate filtering is to find like an internal eigenvector, but assume that you do know what the internal eigenvalue is. But in many cases, you don't know what that eigenvalue is. For example, in quantum chemistry, you're interested in the ground state of a complicated many-body Hamiltonian, just don't know where that is. So you also need to find that ground energy. Obviously, this is a very difficult task because you just find the ground energy of like a 5 local Hamiltonian is going to be QMA hard. So we do have a very crucial assumption, which is that you have a decent initial state. So assume that you have a Hamiltonian H, and we assume the block encoding model called alpha M without loss of generality. We assume there's no error in this block encoding. You have some decent initial state prepared by a unitary called UI. And what you want is to find the ground energy, lambda 0, and the corresponding eigenstate, psi 0. And we here have two key assumptions. The first is that there's a lower bound for the overlap. The initial state and the desired eigenstate, the gap should be decent. And the second is that you don't know what the ground energy is, but you know roughly where it is. And you also know roughly there's a lower bound. So what it means is that I don't know what this is, but I roughly know it wouldn't be too far away from a mu, and it should be gapped by delta. And also this mu is gapped from the first excited state by delta. So what I want to do is, again, to form a step function. It is 1 here and 0 here. If you just do this, that's a formidable task. But since I do know a gap, I can just smoothly do a transition and go from 1 to 0. So the basic idea is what we developed is called the binary search. Sounds like a very simple idea, but I'm going to comment on that later. What you basically do is you construct a polynomial, and for example, like an earth function, and satisfies that here it is a 1, here it is a 0, and in the middle there's some transition. For example, earth function looks like that. And H has this alpha M0 block encoding. You apply this polynomial using QSP to the large with a large overlap, and then you can tell whether roughly it is bigger than x plus h or smaller than x minus h. But there's actually a little problem here, because if the E0 or lambda 0 lies here, you actually don't know whether it is this side or that side. So that's really the problem. How to solve this? It's very simple. You apply two shifted polynomials. They only differ by some tunable parameter called h. What you can do is to return the result from two independent measurements. So let's say if you get, with high confidence, you can say that if it is 1, if it is returned to be 1, then most likely, and it is not most likely, with high confidence, it is going to be bigger than x minus h, even though it might be wrong, but you don't know whether it's here, but it's going to be here. If you measure the 0, then you don't know, again, don't know this side, but you do know it has to be less than x plus h. Now you have narrowed down from a larger interval to x minus h to x plus h, and then you just do a binary search in the middle, and you can exponentially shrink down the interval containing the ground energy. So the idea sounds simple, but it's really achieved so far the best result to our knowledge. Before this, there is, of course, the well-known result is by phased estimation, and there are a number of undesired features due to phased estimation. Other than that, the previous known, best known results are obtained by Ge, Tura, and Sirac in 2019. So they have considered the problem of preparing a ground state with a known bound of the ground energy, finding the ground energy, and prepare the ground state where the bound is unknown. So, so there's a lot of information in this table. I want to say that we use less number of qubits because we use QSP. The most noticeable improvement are that you can see here they achieve this dependence is h to the 3/2, and that is really because we use a Grover search instead of a binary search, and we have improved that to h. And here you again, due to the Grover, there is a square h here, and we have improved that to logarithmic. And also there is a corresponding improvements when you prepare the ground state with an unknown bound. So we can also prove that this algorithm achieves a certain lower bound in terms of the complexity. For example, if the gap is large and the initial overlap is 0, then you cannot use less than 1/gamma applications of UH to get that, and our complexity is 1/gamma. Similarly, when initial overlap is large, but the gap is close to 0, the number of queries cannot be less than 1/delta. We achieve that, and there's a more subtle bound when there's more subtle bound here. So finally, let me talk about some future works. And so there are a lot of challenges. So I also talked with Andrew during the semester. I think I learned a lot. And so the large scale, first of all, large scale fully error corrected quantum computer probably remains at least really, really hard in the near future. Probably not necessarily ridiculously hard, but probably really, really hard. So we want to think about both near-term and long-term goals for the quantum linear algebra. There are a number of topics that are of interest. For example, efficient gate-based implementation of AQC. Recently, in Andrew's group has done this very interesting work of Trotter bound for time-independent problems. How do you generalize that, especially this commuted type of bounds, to do efficient time-dependent simulation? Seems to be interesting. So quantum signal processing has really appeared in a number of, appeared many times throughout the talk, as you have seen. And I think it's really a beautiful theory, and it's very much related to approximation theories in SU2, and converted the problem of a quantum computing thing to a classical computing problem. Here is about how to obtain the phase factors. One efficient approach that is what we have developed quite recently, called optimization-based approach. And but more generally, these are related to this polynomial approximations with the non-trivial constraints. I think there are a lot of things to be studied there. And another thing that we found in this thing is the decay of the phase factors. And there's a close relation between the decay of the phase factors and the regularity of the function that is of interest. I think there's a lot to be studied there as well. So the fast forwarding of certain Hamiltonians, I think that's also very interesting because although there's a complexity theory lower bound, it doesn't mean that no linear systems can be accelerated. So therefore, the fast forwarding and the preconditioning, they really go hand in hand with each other. And one important progress recently is done by Low and Weeb in this interaction picture Hamiltonian simulation. Recently, there has been a lot of interest going beyond linear algebra, but to study the ODEs and PDEs or open quantum systems with quantum algorithms. I think that's rather interesting. But of course, there's a very important question there, which is, I mean, what kind of speed up do we really expect? I think so far, as far as I know, we don't know the answer, and it would be really good to know a clearer picture behind that. So the block encoding model is really my recent favorite, and but I think the power of this model remains to be studied. For example, the block encoding Hamiltonian simulation can be much trickier than the Trotter counterparts. And last week, Yuan Su gave a beautiful talk explaining why this is so. But one thing I'm recently interested in is how do you connect this block encoding type of model with the supremacy type of circuits, which I'm going to talk about a little bit later. And another thing is we have so far assumed oracular type of assumptions, but in the end, when we demonstrate that for some real applications, we really need to get rid of all the black boxes and go to the gray or even white boxes, whether you can still get a good speedups. I think it's an important question. And finally, the thing that we're recently working on and hopefully can get some results soon is what's the proper counterpart of the dense matrices in quantum setting? I mean, there's a famous Lin benchmark, which has been used to benchmark the top 500 computers since 1979, and the impact for the top 500, the benchmark itself started from 1979. The use of it to define top 500 starting from 1993, can we really mimic or replicate its success? And how do we really get those dense matrices? And or what should be the proper quantum impact benchmarks in the post-supremacy era? So here are a few references for the talks. And finally, I'd like to thank you very much for your attention.
Okay, yeah, thanks very much, Lin, for this this nice talk. I mean, thank you on behalf of the whole audience, since we can't have, you can click the applause button if you want, but we can't have the usual sort of applause. But now I think we have time for some questions, if there are some. And I know Nickel had a question during the talk. So I don't know, Nickel, do you just want to just unmute and go ahead and ask?
Sure. Yeah, the question was about AQCX. So the question was, how robust is this result to perturbing the schedule? So does it rely on some very delicate cancellations or something like that? I guess the
as
reason
far as I know, yes. So, because really, as you can see, the schedule is like at the beginning needs to be slow, at the end needs to be slow, and the intuition, I mean, the rigorous proof is always, more delicate, like the Algebra class type of thing. But the intuitions behind is integration by parts. What do I mean is that if you look at this Jensen bond, and there are this integral here, and you set S to be 1, and then you can keep doing integration by parts and raise the power of h, to the boundaries, h power, some derivative of 1, h some power derivative of 0, and they keep canceling, right? Mm-hmm. So in that sense, I do expect that it is kind of delicate. And in that sense, I also think why the Eigenstate filtering seems to be more robust.
So in particular, does that have any implications for the gate complexity of implementing AQCX? Because it seems hard to discretize.
So that's an excellent question. And what we do so far is to quote the low-end weave. And that's actually a rather complex apprentice. And if you read that, there are all sorts of stuff, adder circuits, compression gauges, obvious amplitude amplification. There are a lot of things there. And how difficult it is and or how robust this is, I think that's really a good future direction to do. Yeah.
Thanks.
Thanks. So I think Ike has a question, and then Andres.
Hi, Lin. This is Ike Chuang. Thank you very much for the beautiful talk. I enjoyed hearing all of these and your beautiful ideas too, especially with regard to the use of the double polynomials for binary search. As you know, the quantum Fourier transform and Fourier transforms, fast Fourier transforms in general, are binary searches. And you can show that, for example, the phase estimation algorithm is just an instance of the singular value transform done with powers of the black box. And so one of the approaches I was thinking of for solving this exact same problem, which I did not complete in the same way that you have, is instead of using two polynomials like you've used, I wanted to amplitude amplify. So you use the first polynomial to figure out the general neighborhood you're in, and then amplify that segment and do another polynomial to divide that in two, amplify again and divide in two, and so forth. Another kind of binary search. And if you had the powers of doing the Hamiltonian to some power, then I might also try to figure out when to turn that power up and then search in the new neighborhood. And I'm curious if you thought about those approaches and what you think those might compare with your approach.
So thanks for the question. And I think, I haven't thought about exactly along that line. I think it's maybe also a promising approach to do that. And by doing another search, I guess you mean the Grover type of search thing?
No, binary search.
Only binary. So there's no, okay. Yeah, so other type of polynomials may also work. This is only, we showed one of them, I think, using, the approximation to the ERF function. And but one thing is this, in terms of asymptotic complexity, I think for all the parameters, this is pretty much optimal, but maybe there are other methods that would also achieve the optimal complexity. For your first question regarding the connection to Fourier transform, I think that's a really good question. We actually discussed about it after the first like bootcamp when we were still meeting in person. We did do some QSP calculations for this kind of approximating this kind of shapes. It seems to work, and if you're interested, we can definitely talk further offline.
Yeah, I'm interested in particular because it touches on fast forwarding. You know, if you are given more information about the structure of Hamiltonians, then it makes it easier to use one or another of these techniques. Like you might
using QSP to do fast forwarding.
Both, using the extra information that you're given about the Hamiltonian, and then using, for example, you might be able to compute some powers of H, or make different blocks, powers of H in the blocks, and then use that inside QSP. Or you might be able to use QSP to turn your Hamiltonian, given your structure information, into something a little better, because you can, you know, like invert the sign or something, SIN, not SIGN, and so forth. So I think the more of these kinds of tools one has, the better off we will be in doing something with QSP for fast forwarding.
Yeah, I think this is a very interesting thing. As you probably recognize, a lot of the challenges are directly stolen from your talk, and but this preconditioning thing is indeed what we're working on right now. And I'd like to, if you're interested, I'll be more than happy to talk with you later offline.
Great, let's talk. Thank you.
Bye. Thanks.
Okay, thanks. So I think Anders has that question.
Yeah, thanks for a very nice talk and these various algorithms. So I was interested in the last version of this quantum Zeno effect based implementation, and so like you suggested that it is probably the nicest from an implementation from practical point of view, and so something that I didn't fully understand that when you apply these projectors with the QSP, do you still need to measure some ancilla qubit, or there is no ancilla measurement during these Zeno steps?
Great. Yeah. So indeed, you need to measure the ancilla qubits, but you can prove is that each of, within each of these steps, the success probability is overwhelmingly high. When they multiply together, the success probability obviously will be lower, but in the end, they're still, the multiply together, the probability is bounded by omega 1. For QSP, you always need to measure something, but yeah, so each of this, the success probability is 1 minus a little bit, and that little bit is controllable. That's really
okay.
Yeah.
Well, the reason why I asked, because like current hardware is actually like not really friendly towards measurements that you would do during the computation of the circuit. They tend to measure the whole thing, but okay, like I guess this is like more a long-term talk. So
I think this is not short-term period.
Yeah, sure. Yeah. That makes sense.
Yeah, so the short-term thing, I like the QSP better, the vanilla QSP better. Yeah.
I see. Thank you.
Yeah.
Great. Are there other questions? Okay, well, if not, let's thank Lin again for this very nice talk. I think this was the last talk of the program. So, thanks to everyone for participating, to all the speakers. And yeah, thanks very much to Lin for the talk, and let's maybe give him another round of applause.
Thanks. Yeah, hope you all enjoy the summer. Yeah, so at home. So.